Swayam Prabha. Digital India. Educated India.
Welcome. We will continue our discussion on sprays, but we will switch gears slightly. We will start to look at the insides of some of these atomizers and nozzles. Okay, so, we are going to, for the next few lectures, we will talk of design of atomizers, and we will begin with design of a pressure swirl atomizer. But before that, I want to provide a quick primer on the fluid mechanics of swirl. We will see how swirl in general works. Okay, I will take two kinds of swirls and we will see what it looks like. So, if I take a container of liquid and spin it at some angular velocity omega about a point O. Okay, so, we are only going to look at two dimensional examples to start with, that is sufficient to understand how things work. Okay, so, this is a container that is spinning and it has got some liquid in it. This liquid, at least at the wall, is going to spin with the container and towards the middle it is not going to spin. So, this is one kind of swirl. The other is where I take, let us say, an infinitely big bath of liquid and insert a rod into this and spin this rod at some velocity, at some angular velocity omega. So, in one case I have liquid inside a container and the container is spinning. In the other case I have an infinite bath of liquid and the infinite bath of liquid, I immerse a rod into that bath of liquid and spin the rod at some angular velocity omega. I want to understand what the fluid mechanics is like in these two situations. Okay, and I am going to look at inviscid flow for now, governed by Euler's equations. So, if I write the Euler's equations in cylindrical polar coordinates, I will write the whole thing. This is our famed continuity equation. Okay, so, this is my theta momentum equation. So, what we find here is that I have three quantities u r, which is the radial velocity, u theta, which is the angular velocity in the theta direction, and p, which is the pressure, the fluid dynamic pressure in the hydrostatic pressure in the fluid, and that hydrostatic pressure is represented by capital P, could be a function of r and theta. Now, I am going to simplify these equations from some very simply by making some assumptions. If I assume axis symmetry, now the two kinds of flows I am interested in are these. So, in both these instances, like in the first instance O is the axis, in the second instance this happens to be O, and the axis passes through O perpendicular to the pointing along the direction of the angular velocity vector in both these instances. Now, so if I assume axis symmetry, what do I have? Let us say u r is only a function of r, u theta is only a function of r. I will use the same symbols as there. P of r. So, if I use these axis symmetry assumptions and scratch out terms that are not important, if u r is only a function of r, and I am also going to assume steady flow. Okay. So, things are spinning and we are well past the spin up phase, that is the phase where the fluid was adjusting to a rotating container or a rotating rod, and we are well past all of those transients and we are in a steady mode of operation. Okay. So, if I now go through scratch out terms and put in parentheses why that term is being scratched out, I will start with the first one. This is scratched out because of axis symmetry, this is scratched out because of the transient nature not being present. Again, this is due to axis symmetry. This is due to the transient nature not being present. This is due to axis symmetry. As well, this is due to axis symmetry. So, I am going to take the simplified version of the continuity equation and see where it will take us. It says 1 over r d d r of r u r equal to 0. Now, if I simplify this, I can first of all replace the partial derivatives with total derivatives, because u r is only a function of r. U r can only be of the form C 1 over r. So, if there is a radial velocity to this flow, it can only be of the form C 1 over r. C 1 is some arbitrary constant that is yet to be determined. Now, if I go to the theta momentum equation and see what that will tell us. Now, before I go much further, I am going to invoke let us look at each case separately. If I take the solid body rotation case, or if I take the I will call it the container case. then r equal to 0 is contained inside the domain, because of which the if u r is of the form C 1 over r, then, and this is the only admissible form for u r, if r equal to 0 is contained inside the domain, that amounts to an infinitely large radial velocity at the center line. So, therefore, the only admissible solution C 1 equal to 0, which also implies that u r is identically 0 everywhere. Now, if I go to the r momentum equation, what I have these are the only two surviving terms. So, if u r is equal to 0, then what I have is this further simplifies to rho u theta squared over r. dP dr is equal to rho u theta squared over r. Okay, so, for the case where the axis is contained inside the container, this is the only possibility, and this should look physically familiar, that this basically says pressure gradients balanced by centrifugal force. Now, if I take on the theta momentum, and take the terms that I still have remaining, u r d u theta dr plus u r u theta over r equal to 0. Again, if u r is equal to 0, like for the container, all you get is an identity. So, as far as the Euler's equations are concerned, you really cannot solve for u theta and p. So, you essentially have one equation which says dP dr is rho u theta squared over r, and from there that is the only equation that you have, and theta and p are both separate, are two unknowns. So, in the inviscid case, in an inviscid swirling flow, you end up with one equation and two variables that you really cannot completely solve. Okay, so, there are two forms of, so whatever be the form of u theta over r, you will recover the pressure distribution associated with that is set up by that centrifugal action. That is essentially what this thing, what that equation says. So, any form of u theta as a function of r that you impose, that you impose on the flow field would give you the corresponding pressure field. Okay. So, if I look at what are all the possible physical forms of u theta over r, and this is not coming from inviscid theory, but actually from viscous theory, okay, but we will use it freely here. Essentially what you find is that u theta over r is of the form omega times r plus some gamma divided by 2 pi r. Okay, this is called solid body swirl, and this is called potential swirl. So, if you look at any kind of a swirling flow, remember that we are not restricted to one of these two forms, except in the case of a viscous flow. We will look at that later on, but as far as inviscid theory is concerned, the only thing that you are allowed to conclude is that if you tell me what v theta as a function of r is, there is a corresponding pressure field associated with that, that can be calculated from the radial momentum equation. Okay. So, now let us go back to a pressure swirl atomizer and see what the basic construction of a pressure swirl atomizer looks like, and see where this theory would come in handy. So, a typical pressure swirl atomizer is composed of, let us say, some n number of tangential inlets that bring fluid in. These tangential inlets may be located at a distance d away from this center of this swirl chamber. So, I will just show one of the tangential inlets, because the others are sort of hidden. So, this is a swirl chamber. there is usually a contraction passage. So, all of this, the rest of this nozzle is axisymmetric. So, this is the simplest kind of a pressure swirl atomizer that you will find. Okay, so, if I go back to this case and let us say, if I was to characterize, this is the cross sectional area, this is some width W, and some height h. So, if the depth of the slot is some h and W is the height, W is the width of this passage and V is the velocity coming in, then the total volume flow rate is V times W times h times n. N is the number of tangential slots, V is the velocity coming in, W and h are the width and height of the slots. So, if I look at what the possible velocity field here would look like inside, and I am going to include this dimension r sub s as the radius of the swirl chamber. Now, if V is the velocity here, one could imagine an invisible container between this point and the center line that is spinning at a linear velocity V or an angular velocity V over d. So, this part would have a velocity profile that looks like that. Okay. Now, if I look at what is happening outside here and if I draw a zoomed out picture, past this point you essentially have to go all the way to the wall. So, this is the wall of the swirl chamber. Now, from this point where you have this tangential slot coming in to there, it is like you can imagine an invisible rod that is spinning at an angular velocity V over d. So, as far as this part of the fluid is concerned, it is like it is being driven by a rod of diameter 2d or radius d that is spinning with an angular velocity V over d. So, this part of the velocity profile is going to look like a potential swirl. So, you have two parts, you have this solid body rotation on the inside and a potential swirl kind of a flow on the outside. So, this part looks like V equal to R omega, this part looks like, or rather u theta equal to R omega, this part looks like u theta equal to gamma over 2 pi r. See, in reality, as you go close to the wall, you also have like a boundary layer, that is due to again viscous effects. So, we will sort of try to stay away from that for now. We will look at viscous effects in an empirical fashion a little later on. So, now if you look at what this flow is doing, total angular momentum coming in is m dot times V times D. M dot equal to rho times Q, that is equal to rho times V times W times H times N, the number of slots. Rho is the density of the fluid. So, this is how much angular momentum is being input into the swirl chamber. So, if I were to draw a control volume around this part, if I do an angular momentum balance on this, because we are looking at an inviscid flow, the walls are not exerting any kind of a torque on the fluid. So, whatever angular momentum comes in is exiting from the bottom. Okay. So, if the total angular momentum coming in is of this form, we will call this I dot in, I dot out is equal to m dot times V at exit times D at exit over 2.